In this video, we'll cover which assumptions and conditions we need for each inference method, along with how to choose which method we'll use. To start, the minimum number of conditions that you'll check for any confidence interval or hypothesis test is 3, and sometimes we add on a fourth condition. However, this is really used to justify two underlying things. The first is that our subjects in our sample are independent, and we have a distribution that we can approximate with a normal model. Two conditions that we always check for every test are randomization. Usually this is just stated in the problem that it's random. If it isn't stated, we want to say something like we assume the sample is representative. Note that if this is an experiment, we're not looking for the subjects to be selected randomly, we're looking for the treatments to be assigned randomly. The second condition that we always check is the 10% condition, saying that our sample is less than 10% of the population. These two conditions are both justifying that the subjects in our sample are independent. They were collected randomly, and they're less than 10% of the population. Their responses should be independent of one another. Now, the next condition is about normality. Can we use a normal distribution to model the problem? There's two different ways we can check this, and it depends on what type of data we have. So to start with categorical data, this is when we have a proportion. We're going to check the success-fail condition. We want to see, do n times p and n times q both equal values greater than 10? This is what we would check for a hypothesis test. We get that p right from the null hypothesis value. NP hat and NQ hat is what we would use for confidence interval, and we use the data from the actual sample. This is verifying that there's enough data in the tails of our distribution so it actually fills out that normal curve and allows us to model it with that normal distribution. If we have quantitative data, this is when we have means. We're going to check the nearly normal condition instead of success fail. We wouldn't be able to check success fail because we don't have a P or a Q. If we're given data here, we're going to make a normal probability plot. We want to see something that's in a reasonably straight line. If it is, we're going to say it's reasonably straight with no outliers. If we're not given data, we want to check the sample size. If it's larger than 30, we can say the distribution is approximately normal under the central limit theorem. If neither of those things are true, sometimes it just says in the problem the data are approximately normal. So those are the three main conditions: randomization, 10%, and then either nearly normal or success fail. If we're dealing with a problem that has two samples, there's a fourth condition. It's the independent groups condition. We want to say the first group is independent from the second group with respect to whatever our response variable is. If it's a quantitative problem, there's also one other thing that we have to check. We want to see if our samples are linked in some way. So maybe we're dealing with responses on husbands and wives or twin brothers, or most commonly before and after readings on the same subjects. If there's a relationship similar to any of these, we're going to check a matched pair condition instead of independent groups. They won't be independent if it's before and after on the same subjects. So instead we say these aren't independent, they're linked, they're paired data. Okay? If they aren't linked, we check independent groups just like above. State the two samples are independent with respect to the response variable. So those were the conditions. Now let's go on to naming the inference method. We have to be able to choose which method we're going to use to be able to figure out which conditions we would use. So there's three questions to determine which inference method we'll use. First off, we want to see, do we have categorical or quantitative data? Do we have one or two samples? And is it asking for a hypothesis test or a confidence interval? Is the data quantitative or categorical? Quantitative data is numerical. It can be given as either raw data that we make a list with in our calculator to get the mean and standard deviation, or it just gives us the mean, standard deviation, and sample size. These are our t-tests and t-intervals, whether they're one sample, two sample, or matched pairs. Categorical data is non-numerical. It'll be given either as a percentage or counts of subjects. For example, 9 out of 90 subjects improved. We would make a fraction out of that to get 10%. That would be our p hat. These are one proportion and two proportion z-tests and z-intervals. Once we have that figured out, we want to determine how many samples are there. Is there one sample or two samples? Special case, when we have a quantitative problem with two samples, we want to see, are these samples linked in some way? If the samples are naturally linked, that's a matched pairs problem. Otherwise, it's a two-sample t-test or a t-interval. Lastly, is it a hypothesis test or a confidence interval? If you're being asked a yes or no question, that's a hypothesis test. A lot of times it'll start with, do the data provide convincing statistical evidence, ... If you're asked to estimate a parameter or the difference between two parameters, it's a confidence interval, such as estimate the true mean SAT scores of students from Tom's River. So with all that out of the way, let's go over some examples. Do people smoke less when cigarettes cost more? We have a random sample of 500 smokers. The number of cigarettes each person smoked each day was recorded. So we're talking about a number of cigarettes. This is quantitative. It was recorded over a 1-month period before a 30% cigarette tax was imposed, and again for 1 month after. So we have two readings on these same 500 smokers. It's a quantitative question. We're counting how many cigarettes they smoke, and it's asking, do they smoke less when cigarettes cost more? Okay, it's a yes or no question. This is matched pairs because we have both these readings in the same 500 subjects. Matched pairs t-test. Our conditions, randomization, 10%. Quantitative, we check nearly normal. And it's the paired data condition because they're linked. This is the only one I'm going to write out all these conditions for. So 500 smokers are randomly selected. It states that in the problem. That's less than 10% of all smokers. 500 smokers is large enough for the distribution to be approximately normal under the central limit theorem. You can just abbreviate that CLT and they'll know what you're talking about. And lastly, there are two readings on the same 500 smokers, so this is paired data. Next up, you have data on rainwater collected at 16 locations in the Adirondacks. One measurement is the acidity, measured on a scale of 0 to 14. Estimate the average acidity. So our actual response variable is the acidity on a pH scale. It's numerical, 0 to 14. We have one sample of 16 locations, and it's asking us to estimate the average acidity. This is a confidence interval, one sample, t-test because it's quantitative. I'm sorry, t-interval because it's quantitative. We're going to check randomization 10%, and then our third condition, nearly normal for quantitative data. We don't need the fourth one because we only have one sample. Next up, how much greater is the percentage of senior citizens who attend a play at least once per year compared to the percent of people in their 20s? We have two random samples, one of 100 senior citizens and the other of 100 people in their 20s. So we have two groups here. It's talking about the percents of people in those groups. So this is a proportion problem. It's categorical data with the underlying question being, did you attend a play, yes or no? Lastly, it's asking us how much greater is 1% than the other. So in other words, we're estimating the difference between these two population parameters, these proportions. So this is a two proportion Z interval. Again, we always check randomization in 10%. Since it's a proportion problem, we're going to check success fail. And remember, when we have two sample groups, we have to check these for each sample. So we do those 2 times each. And then lastly, independent groups, we always check that when we have two samples, either that one or possibly paired data if it's quantitative. Lastly, Consumers Union wants to see if one brand of calculator is easier to use than another. We have a sample of 100 volunteers. We randomly assign them to 2 equal-sized groups. One gets calculator A, the other gets calculator B. Researchers record the time required for each volunteer to carry out a routine set of calculations. So we have one sample of volunteers, however, there's randomly assigned to 2 groups, and that's the important part. That's also why it doesn't matter that they're volunteers, because we're randomly splitting them up. So we have our calculator A group, calculator B group, they're both size 50. They want to see, is one easier to use than the other? Okay, now the main question at this point is, are these samples independent or are they paired? Since they are randomly assigned, they will be independent of one another. So this is a 2-sample t-test. Randomization 10%, nearly normal. Again, we have to do these 2 times each, one for each sample. Okay, they're both 50, size 50, sample size 50. So we would say that the central limit theorem applies. They'll both be approximately normal. And then lastly, check independent groups. The times using these calculators for one group is independent of the other.